Okay, so this is Speedrunning linear algebra, and the whole point of this is that it forces me to explain concepts that I learned a long time ago, and that it might be fun for my friends watching me. But the point of this is not really to teach linear algebra. For that, you should watch the 3 blue, 1 brown videos, from which I've heavily borrowed. But I'm going to be explaining 3 basic concepts in linear algebra, starting with vectors and this idea of the span. I'm going to talk about what matrices are from a geometric perspective, and then I'm going to talk about the determinant. There were other things I wanted to talk about, but I realized I was not good enough at explaining it for it to make sense. So, vectors. Normally understood as like a coordinate with an arrow. So like the common physics perspective for a vector is that, it's literally a coordinate with an arrow. So this one is 2 over 3 up. Another way of describing it is using this idea of the unit vectors, which is I hat and J hat. And I hat is the unit vector that goes along the x-axis, and J hat is the unit vector that goes along the y-axis. So that's kind of a physics perspective, but another way you can think about vectors is just as almost like a list. For computer scientists, you can talk about vectors as containing different types of information. So it can be like the price of a house, or someone's name, if you have a translation scheme between the alphabet and numbers. So that's more like how computer scientists think of it. And that's cool later on, helpful to keep in mind for when you actually try to apply linear algebra. Okay, so vectors, linear combinations of unit vectors. Now I want to talk about this idea of the span. So a span just refers to the space of the whole. This is Alex. Alex is down there. He was saying ni hao. Yeah. Like I said, this is a really shitty explanation of linear algebra from 5 hours of restudying it. But so I've talked about what vectors are linear combinations of the basis vectors, which is I hat and J hat. The idea of a span is the whole space that a set of vectors can address. So in the case of I hat and J hat, which are these little unit vectors, the span of I hat and J hat would be this whole 2D plane. So x, like every single vector here can be addressed by I hat and J hat. And that's because they're orthogonal. This is probably wrong notation, but I don't care.
Questions, or do you want to save them for the end?
Yeah, can you save them for the end? Because I think the video is like harder to watch if there's questions. It'll be fairly short. But so the span of these 2 vectors is going to be the entire 2D plane. But if you want to talk about the span of a single vector, like of 2, 3, that's just going to be any linear combination of this vector. So that means that in practice it's going to be the line that 2 and 3 lies on. So if you multiply by 0, you get here. You multiply by a negative number, it goes down. But yeah, the span of a single vector is going to be the line that it lies on and goes through the origin. Okay. So that's simple notion of what vectors are, notion of what spans are. Now we can talk about what matrices are supposed to do. So matrices are composable linear transformations of vectors, but you can understand them in different ways. Usually when they're first presented, when it was first taught to me, this like very first matrix I saw was just, it was a big square and there was a bunch of numbers. And they were pixel values of an image. And so that kind of refers back, that's like not the most helpful way to understand it, but I think it is like the default way. A more helpful way to understand it is as taking these vectors and moving them around in their span. So the simple example of, just to clarify what a matrix is supposed to do, is this 2 by 2 abstract matrix. And these letters can be any number. And what you should understand this matrix is doing is this first column basically tells you what happens to the I hat unit vector, and then this second column tells you what happens to the j hat unit vector. And to illustrate that, here's an example of a linear transformation that rotates a vector. So 0, 1, minus 1, 0. So what do I mean by what happens to I hat and what happens to j hat? Well, as I hopefully mentioned before, I hat is 1, 0, which means it looks like this. What happens to I hat means that all of the components that lie in this I hat axis become like 0, 1. So in effect, all of the components here rotate and start to face upwards. And for j hat, all the components that are facing upwards become this -1, 0. And let's take our vector here. So we have 2 and 3. How we get the resulting vector is it's this I hat component scaled by the amount that you multiply I hat by, plus the j hat component multiplied by this right-hand vector. What we're going to get is, -3, 2. And that is going to be 1, 2, 3. It's -3 and 1, 2, which looks like this, which is a 90-degree rotation. I changed my mind. If you want to ask questions, you should ask questions, because then it's more fun. Yeah. Okay. So that's a basic idea. A matrix is something that does something to a vector, or that does a linear transformation to a vector, not just anything. You can think of it as a single point, but then you can start to think of whole shapes too. Like if you wanted to apply this matrix, this function, to like a smiley face on this plane, after applying this rotation, you will get a smiley face that looks like this. Yeah.
Is there always a rule that the vector goes after the matrix?
Yes, that is a rule.
Is there a reason? No.
I mean, I think, well, there is some reason. I think it's more like a convention thing. Do you have any sense of this, Sebastian? Like it's just to make it work. You have to, it can either go like before or after, but when you're doing things with different dimensions, You know, this is like 2 by 2, and this is,
They have to agree on like the type, right? Like the number of rows of the left one has to equal the
Right.
the number of columns. The number of columns of the left one has to equal the
the
number of
rows on the right one. Because,
if you
yeah.
flip the order, you would not match.
Yeah, because then you don't have, this whole operation of multiplying matrices by vectors is only defined for,
Right. So, it's not fun. So basically, the two inner number, let's say.
yeah, have to match.
Okay.
Yeah. Okay, so you can think of this as like a way to transform vectors or sets of vectors in some way, in any like linear way, which can be a rotation, shearing, expansion. And an example of another matrix that does something is like this 2, 0, 0, 3. And what this is going to do is expand the I hat, make it wider 2 times, and then make it taller 3 times. So what you're going to get is, you're going to get, like you can do the math later, but what you will get is a vector that is 1, 2, 3, 4, then up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like here. And that's in a line. This is all in a line. Okay, so matrices are like functions that do stuff to sets of vectors. But what about when you combine matrices? Like, what are you doing when you're multiplying 2 matrices together? Well, you can just think about that. Naturally, you can just think of it as combining the transformations. So if you want to, keeping in mind the rotation matrix, 0, 1, minus 1, 0, and then this expansion matrix, 2, 0, 0, 3, when you multiply these together, you're going to get a new matrix, which is the result of first rotating it 90 degrees and then expanding it. Does that make sense?
Yeah.
So there's like, I'm trying to do as little math as possible because that's the part that takes a long time and is not that intuitive. But yeah, you can.
So are there some rules that from ABCD you can tell how the transformation is gonna be? Like this example that we gave you have this 2, 0, 0.
Yeah, so the determinant kind of helps you understand that. It's like pretty not obvious. So the general principle is like what I mentioned before. This is what happens to the I hat dimension. This is what happens to the J hat dimension. So that's how I knew that it's going to get 2 times wider, because all this is doing is like multiplying I hat by 2 times.
Right.
But if you have something really funky, like 3.5, negative 2, and then 7,
Right.
negative 8, then it's doing something much weirder that like you don't really know. It's like a rotation or whatever.
Can
So-
you learn how to multiply these matrices? Is it the columns times the rows, or?
Yeah, so it's like this action. The multiplication rules. So if we go back to in abstract how to multiply matrices by vectors, you can generalize that to figure out how to multiply matrices by matrices. So A, B, C, D times like X, Y is just going to be AC times X plus Y times BD, right? Does that make sense? Because the X is the multiple of the I hat unit vector, and then Y is the multiple of the J hat unit vector. So if we want to now do A, B times C, D, then multiply that by E, F times G, H, what we're going to get is I want to make sure that I do this in the right order. What we're getting is we can think of it in terms of two components, which is like the I-hat transform. And that's going to be just this component multiplied by this. So you can think of two matrices as first doing a column, like a vector multiplication with EG, and then doing a vector multiplication with FH. So the EG is going to explain what the I-hat component is going to become. And that's going to be like this. It's going to be E times A plus G times B, right? Because, so right now it's just like subbing in E and G for X and Y here. So it's going to be E times A plus B times G, and then it's going to be E times C plus G times D. So this is just the vector multiplication of EG and ABCD. And you just do the same with the right-hand side. Let's where's space?
But isn't the result going to be a 2x2 matrix?
Yeah, it is.
Oh,
So
okay.
this is just the left, this is the
Oh,
column.
okay.
So the right column is just going to be A times F.
Interesting.
Yeah, FA plus BH, and then FC plus DH.
And does it generalize to any number of columns in the second matrix? So if I have a 2x2 by a 3-column, 2 rows, the same thing you explain applied, right? So
Wait, so if you have a 2x2,
so the first number is rows, right?
yeah,
So a 2x2 times a 2x3. Does this pattern explain generalize, where I can just treat the 2x3
yes,
like 3 2x1?
yes. This is a result of it being a linear transformation, because then you're summing up the different components.
So is it true that the result of the multiplication of that one is going to be a 2x3?
Yes, but that doesn't. Yeah, it is, but yeah.
I was trying to understand what's the rule that makes me figure out what's is going to be the final dimension.
Oh, it's just the outer ones.
Oh, okay. I see.
Yeah. I don't really have a particular intuitive. I mean, so here's what you can think of it actually as. So like a 2x2 is just taking a 2D projection and mapping it into 2D, and then a 2x3 is taking something that's in 2 dimensions and then mapping it to
Oh, interesting.
something that's in 3 dimensions, right?
I see.
I mean, wait, actually, is that reverse? Taking something in 3 dimensions and mapping it to 2 dimensions. Wait, so if it's like a 1 by 1 times a 1 by 3, what you're gonna get is a 1 by 3. Yeah, wait, isn't that right? Like a 1 by 3 takes something in a 1 dimension, then maps it to 3 dimensions.
Which one's which? Is it row by column?
It's row by column. So, but I'm just thinking of like the shape of the outputs. Like, so if you think of a vector that's like 1, 2, 3, and you think of a 1D point that's just like 2, and then you multiply it, and that gives you, 2, 4, 6. That's like a point in 3D space, right?
Well, the scalar 2 is not a 1 by 1 matrix. It's just a 2. I don't think you can put a 1 by 1 matrix there because it's a type error.
This is so.
Oh, right.
Oh, you're right. This is a 3 by 1. Okay. Yeah. Yeah.
Yeah.
And this is the number of dimensions. Otherwise, it's yeah. Okay, you're right. like you don't treat this. So what I was saying before is like that, but this isn't like a vector. This isn't like a vector in 3D space, right? This is like a matrix that's 1 by 3. Would you agree with that? Yeah. Does that make sense, Alex? Like, so the row, so a column like specifies a point. Yeah. A row is not a vector. Yeah.
It's sort of a pun with like a 1 by 3 matrix versus a vector.
Uh-huh.
You know, you use the same notation for them actually. And that's because you can actually sort of canonically identify a vector with a linear map from a one-dimensional vector space to your vector space.
Mm-hmm.
So a linear map from real numbers to 3D space,
Mm-hmm.
you can canonically identify that with a vector, which is where does 1 go?
Mm-hmm.
0 gets sent to 0, 1 gets sent to some vector.
This vector, right.
So you can...
Oh, so you're explaining how you can link a 1 by 3 with the 3 by 1? It's like there's like a...
I've already forgotten which one's on the left and which one's on the right. My point is, like, your xy vector,
Yeah.
you're using the same notation as if that was like a matrix,
Uh-huh.
with 1 column and 2 rows, and like you kind of silently did this, right, which is fine,
Uh-huh.
but it's justified because you can actually like identify them and you get the same rule. Like,
Okay.
like if you try to apply the matrix to a vector, you get some formula. If you apply to multiply those as matrices,
Mm-hmm.
you get some formula, and they happen to be the same formula, so you're okay.
Huh.
Right? But like,
Okay. Okay.
And that's what canonical means?
yeah, canonical is like there's kind of only one way to like identify them.
I see. I see.
So
Okay. So this is the basic notion of matrix multiplication. Oh, and one thing that I want to mention before going to the determinants is this idea that like the ordering matters. So it matters if you first rotate and then scale. Well, actually, it depends on the exact operations, but in general, it's not like you won't get the same matrix if you swap these.
Right.
Yeah, and so one trivial example that Sebastian demonstrated is what you can do is stretch the y-axis and so like if we care about 2 operations, one is rotating at 90 degrees, which is like 0, 1, minus 1, 0, and then stretching the y-axis, which would be 1, 0, 0, 0, 2, versus doing the opposite, 0, 1, minus 1, 0. You're going to get 2 different things. So if you first stretch the y-axis, you're going to get a stretched smiley face like this. And then rotated, it's going to become like that, right?
One day and stretch it.
Yeah.
I see.
But if you first stretch it, or sorry, if you first rotate it, then you're going to get, this shape, and then stretched, it's going to look like this. So one is a bigger smiley face.
Interesting. And this applies to all the transformations, or?
No, so there are some transformations, there are some matrices where it doesn't matter which order you use, but in general, this just shows you that there are cases in which the order does matter. And if we do the math, like if we multiply these, you will get different matrices. Like this is 0, -1, so this is going to be -2 and 1. Wait, sorry, that's not. 0, I might just do this math like a little bit later, so it doesn't take too long. But yeah, you can do the computation, and I guarantee you they will not be the same matrices. Okay, so that's basic notion of what matrices like are. That is more nuanced and hopefully more helpful than just thinking of it as a collection of numbers that you can apply these rigid rules to. Now, the final thing that I know how to talk about is determinants. So I mentioned before that you can think about matrices as mapping specific points and doing things to them, like rotating them, but you can also think about shapes too. Like taking a circle and stretching it out or making it smaller. And the simplest shape we can do is just the unit square, which is going to be this little guy here. The most helpful way I know of thinking about the determinant is how does the area change of the unit square when you apply a particular matrix to it. So say we want to do this scaling thing again. 2, 0, 0, 3. And the corner of the unit square is going to be the unit vector 1, 1. And we're just going to get 2, 3. So it's going to go from here to 1, 2, 1, 2, 3. So it's going to become this size. What the determinant tells you is like for any given shape, how many times bigger it's going to become. So from here you can kind of tell that there are like 6 unit squares that can fit into here, right? So you know it's like 6 times. What the determinant gives you is, a way of doing that for any matrix, not just this relatively simple one. So in this case, the determinant of 2, 0, 0, 3 is going to equal 6. But I presented this in the wrong way. In general, people teach the determinant as like a formula that is for a 2 by 2 matrix, like AD minus BC, but that doesn't mean very much until you start to think about like the way that the area corresponds to it. And like to get a good intuition for why this is the formula is, I think takes a little while, but some informal intuition is that you can think about this as scaling, like multiplying the width and the height of the unit square, and then BC is doing something with like the diagonal line and like the shear of the shape. So, and I chose this case because it's easy you can just ignore BC basically. And you can see here that any matrix with zeros here in the bottom left and top right, like the determinant is just going to be the product of like how much I hat is scaled and how much J hat is scaled. But yeah, when you start to add other numbers, there's like shearing factors and whatever. Oh, and also you can get negative numbers with the determinant, right? Because BC can be bigger, obviously. And if you take the absolute value, that's still going to be the scaling factor of the shape. But one way of thinking about it is like the geometry or like this whole page is like inverted when you actually get a negative determinant, or like that's what the matrix is doing.
A negative determinant means it's shrinking, right?
No, not necessarily. A determinant less than 1 means you're scaling it down, or like between 0 and 1, or actually the absolute value of the determinant between 0 and 1 means you're scaling the shape down. But if it's negative, you can still be scaling it up, but it's just like the points get inverted. And so the point that should be here, it'll be going in the other direction.
Oh, that's interesting. Right.
And
so if I get it in between -1 and 0 means it's shrinking, but in the other direction.
Yeah. Yeah. Or there's like a flip and it's also shrinking. And so the determinant is something that it ends up being super helpful for finding like the inverses of matrices. Like you usually do 1 over the determinant times this like series of operations, but also for just like many different things. Also finding like the eigenvalue and eigenvectors of matrices, which I am not going to explain today, but
it sounds helpful if I want to figure out just from the numbers what's going to happen to my vector.
yes.
It sounds like I can just look at that determinant and have a guess of what's going to happen.
Yeah, yeah. Well, you can, yeah, definitely it does tell you, like, it can tell you things like if your matrix is invertible also, and whether you can do these other operations to it. But yeah, in general, the determinant is pretty useful. Yeah. So, okay, so...
What do you mean by whether it's invertible?
So I didn't line up a explanation of like inverting matrices, but informally, so if every matrix does an operation, to undo the operation, you need to find the inverse of the matrix. And there are a series of like computational steps you use to do this. But like, I'm not going to go into those computational steps, but to do that, you do need to find the determinant usually. But yeah, the inverse of every matrix is just defined as the thing, as the other matrix, which when you multiply by it equals the identity. And the identity is just another name for the unit vectors, like put together. Yeah, which in 2D is 1, 0, 0, 1. Yeah. Okay, so that's determinants.
And does the determinant generalize? I mean, does this concept of the area generalize to more dimensions?
Yes.
So it would be like the volume.
Yeah.
Of the
exactly.
unit
Yeah.
Cube.
Yep. Yep.
But then, how does it work in 3 dimension if you go negative?
Yeah, that.
It turns inside out.
Actually, I've not. I saw the visualization and I have like a pre-verbal sense of it, but I don't really know how to like explain that. I think it's helpful. It's like most helpful to look at one of these computer visualizations of it.
What was the question?
It's like a negative determinant in 3 dimensions. Like what is that?
What happens to the volume? It becomes like a negative volume in the sense that
Like the orientation changes.
all the surfaces, right?
Yeah, so, you know how like your hands are different orientations, right? Because you can't rotate your hand into your other hand. It's like, right? They're mirror images, so you can't actually rotate them into each other.
Interesting.
Mm-hmm.
I like this concept.
So, a linear transformation with a positive determinant would be like a rotation or scaling of your hand. But something with a negative determinant would also kind of take the mirror image so that it would be like your left hand side.
Wow.
So that's pretty cool explanation. So
Yeah.
if I get a linear transformation in 3 dimensions of my hand that has a determinant of -1, I get my other hand.
Mm-hmm.
Pretty crazy.
The final thing that I can briefly talk about is this idea of changing basis. And I like it because it's kind of Buddhist to me. But, so we've been talking about the unit vector as like, the unit vectors are like I hat and j hat, which in our world is just 1, 0, and 0, 1. But you can think of like an alternate coordinate system where everything is slightly different, and how it might how you might be able to visualize it is just like, well, actually, I don't know if I can draw this well. It's like, this is too hard to draw. But you can imagine a world in which you don't use these as the unit vectors. So you think about every other vector in terms of combinations of another basis. It sounds very abstract, but one fairly easy example is you can think about looking at the shadow of a shape. So a square like this, or like, I guess, a cube, can cast, if light is facing it this way, can cast a shadow that looks like that. If you want to get the area, like say you can only see the shadow because you're like looking down at the cube, but you want to understand where, like, what the area of the shape is that's facing the light. One way to do that is to figure out the projection of this shape onto this shadow. And this notion of like changing basis vectors is helpful for that. And I don't have like a concrete example with numbers, but a like really simple arbitrary change of vectors could just be you choose one that's like 1, 2, and then 3 minus 1. Say that like, this is the shadow world. So you could imagine someone finds the matrix that like maps a shape onto this shadow, and the matrix is like this. It's like 1, 2, 3, -1 for some reason. Then what you can do to change your world to that world is to think about 1, 2, and 3, -1 as like mappings of 1, 0, and 0, 1. Right.
I'm confused about dimensions here.
Yeah, and this is maybe a bad example because it should be like a 3-dimensional matrix. You're right. So it should be a 3 by 3 thing, right? If we're talking about.
Or if you're mapping 3 to 2, then it should be.
Oh yeah, it should be.
3 by 2.
Two
It should be a
rows,
3 by
columns.
2. Yeah. So like a 1, 2, 4. Yeah.
Other way.
Wait, three rows by 2 columns. 3 columns by 2 rows. Something like that.
Yeah, 3 rows by 2 columns.
3.
Whatever you just wrote is right.
2 rows by 3 columns, yeah. So this would, yeah. This is the matrix that would take our world of, our world of 3 dimensions, where this is the unit vector, and tell us how to get to the shadow world. Yeah, so it's like it's a function into the shadow world. And well, the Buddhist part is that like realizing that any coordinate system you have is like relative in some sense, and it's like you can just translate freely between the bases. Yeah, and that's what was cool to me. Like it's equally valid in some sense, and you can just create mappings between different bases. So like it's like I chose bad examples, but if you just remember, if we just think about the 2-dimensional and kind of ignore the shadow for one moment, you can have another basis that's like this, 3, -4, and you could think of a vector like 3, 2 as being equal to 3 I hat plus 2 j hat, or being just equal to, if we name these like b1, b2, we could think of it as just being equal to b1 plus b2.
So basically, each vector can be represented in terms of the basis.
Yeah, in terms of
All,
basis, which you can
all the
choose. Yeah.
So is it even legit to represent a vector just with two rational numbers, or is there always like a assumed base?
Well, the assumed basis is usually the unit vectors.
Right.
But if you're in a scenario where there's two different like surfaces that you want to map between, then you want to change the basis for that.
If you're speaking about linear, if you're speaking about geometry, I guess there's always an assumed base when you write down a matrix.
Yes, which is the unit vector
Right.
base
So that's
basis.
assumed.
Yeah.
So if you want to write them explicitly, you should always write 3i, 2j. That's what you're omitting.
Yeah. 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 So I think that's basically what I wanted to talk about for today. But for a recap, talked about vectors, the two perspectives, what a span was, that the span of the unit vectors is the whole plane, and the span of a single vector is the line on which it lies. We talked about matrices as composable linear transformations. So it can be like rotations or shrinking, shearing, stuff like that. We showed how to multiply a matrix by a vector, and how to multiply matrices together. And we talked about the determinant as a way of finding the scaling factor of a shape. And then we talked about changing bases as a way of going to the shadow world. Yeah. Wait, what? Is that a question?
Yeah.
What's the question?
So in all the examples, you're speaking about changing like a smile or a circle or a
Mhm.
cube.
Yeah.
But I guess all these structure are actually represented by functions, right? So how?
I mean, they don't
actually
have to
work?
be
'Cause,
represented
you're
by
giving an
functions.
example with what I would think is points all the time. So
Right.
how would you apply a linear transformation to a function or to a structure applied to a function? If I actually want to do what you told me about taking the shade of the cube, the cube I guess is represented as a function, right?
Yeah, I mean,
Cube, I don't know, let's say a sphere, so it's easier.
right.
If I want to get the shape of a sphere, I need to apply that matrix.
So Sebastian's definitely the one who could give the better answer to this, I think. But like,
Are there only
What do you mean by function?
so it's like, so I think,
You mean like x squared equals y squared?
Yeah.
yeah. How do you think about linear transformations of
Well,
that?
let me simplify a smiley face.
are they the parameters of the? Yeah.
So this is you're like, this is a circle, but like it's not a circle, it's an equation. Right, okay, what is a circle is like the set of vectors x, y,
Right.
such that x squared plus y squared
Yeah.
equals 1. So it's really a set of vectors. And then to
So,
apply,
okay, I see.
to apply f to this is to say, you know,
Yeah.
apply f to all of these.
Right. So how do I practically use a linear transformation expressed as a 2x2 matrix to that equation? If I want to find the equation that represents the stretched sphere, and I have the matrix.
Oh, you want the new equation?
Because it looks like